All right, so you've probably heard all about AI that can predict the next word in a sentence, right? But what if an AI could predict the next event in the world? We're talking about a whole new frontier today, AI that literally builds its own internal simulation of reality, just to understand cause and effect. This is some serious stuff. Let's get into it.
I mean, just think about that for a second. An AI that doesn't just react to what's happening right now, but one that's actively predicting what's going to happen next. It can run through thousands, maybe millions of what-if scenarios inside its own head, all before it even makes a single move in the real world. That right there is the huge promise of what we call world models.
You know, it's funny, because our own brains do this all the time without us even realizing it. Think about a baseball player facing a 100-mile-per-hour fastball. They don't have time to sit there and do the math, right? There's just no time. Instead, their brain is running this incredibly powerful internal model, one it built from years and years of experience to predict where that ball is going to be. And that's exactly what AI researchers are trying to do here, give machines that very same predictive superpower.
So here's the really crucial point. A world model isn't some program where engineers sat down and typed in all the laws of physics. Not at all. It's a neural network that actually learns the rules of its world just by watching it. It basically builds its own little miniature universe inside its head that it can then play around and experiment in.
And look, this is a massive, massive leap from the large language models, the LLMs that we're all getting used to. An LLM is basically a master of matching patterns in text. A world model, though, it's trying to build a real, genuine understanding of cause and effect. You know, it's the difference between knowing the word gravity and actually learning what gravity does to things in the world.
Okay, so how on earth do you even build one of these artificial minds? Well, the foundational recipe for a lot of their early world models is this really elegant but powerful architecture. It's called the VMC framework.
So what it does is break the AI's job down into three main parts. First, you've got the vision component. This is kind of like our eyes. It takes in all the raw data, like the pixels from a screen, and squishes it down into a much simpler, abstract idea. Then, that idea goes to the memory component. This is like our short-term memory. Its whole job is to look at that idea and predict what's going to happen next. And finally, you have the controller. That's the decision maker. It takes that prediction and uses it to pick the absolute best action. So it's vision, memory, controller. Or even simpler, see, predict, act.
Now here's where this whole field gets really, really interesting. It's not like there's just one single way to build these things. Nope. There are actually several competing philosophies, almost like different schools of thought, on how an AI should imagine the world. So let's break down the three big ones.
First up, we've got what's called the generative approach, and the poster child for this is a family of models called Dreamer. Its whole goal is to create this super rich, detailed simulation of the world inside what's known as its latent space. And that's just a fancy term for a compressed, abstract version of reality that lives in its own mind. The crazy part? It then learns pretty much entirely inside that dream, playing out millions and millions of scenarios before it ever has to do a single thing in the real world. And the progress here has been absolutely staggering. I mean, in just 4 years, the Dreamer series went from doing simple little tasks to flat-out beating human players at Atari. And then by 2023, Dreamer v3 tackled one of the most complex challenges out there. It figured out how to gather diamonds in Minecraft completely from scratch. And you gotta understand, this isn't just about playing a game. This shows it can do long-term planning and use tools creatively, all without a human ever showing it how.
Okay, so the second approach is a lot more, let's say, pragmatic. It's a model called mu0, and it kind of asks a totally different question. It says, hey, what if the AI doesn't need to dream up this whole picture-perfect world? What if it only needs to predict the stuff that's absolutely essential to winning? Things like the future score, how good its current position is, and what the best next move would be.
And let me tell you, this super lean, focused approach is unbelievably powerful. It's the secret sauce behind the AIs that achieve superhuman performance in games like Go and chess. But there's a catch. Because mu0 never has to check if its predictions actually match what the world looks like, its internal model can just drift away from reality. It might end up learning some bizarre winning strategy that relies on a rule that doesn't even exist in the real world. It's like it's chasing a ghost in its own machine.
And that whole idea brings us perfectly to our third philosophy, which is championed by AI pioneer Yann LeCun. His argument is pretty compelling. He says that trying to predict every single pixel of the future, like the exact way every single leaf on a tree is going to rustle, it's not just impossible, it's a complete waste of computational energy. He believes a truly intelligent system only needs to understand the abstract consequences of an action.
And that philosophy is perfectly baked into his architecture, which is called JEPA. It stands for Joint Embedding Predictive Architecture. Now, instead of trying to generate a whole future picture, JEPA learns by predicting a compressed, abstract representation of what's going to happen. Think of it this way. It's not trying to paint a photorealistic image of a ball falling through the air. It's trying to learn the actual core concept of gravity.
Okay, so let's just recap these three big ideas real quick. You've got Dreamer, who is like the generative artist, trying to create this rich internal dream of the world. Then you have Muso, the pragmatic gamer, who only predicts what it needs to win, nothing more. And finally, there's JEPA, the abstract physicist, who's totally focused on learning the underlying rules of reality, not just the pixels on the screen.
But of course, none of these approaches are perfect. Not by a long shot. Building an AI that can genuinely imagine things is incredibly, incredibly difficult. And one of the biggest hurdles they face is this really subtle but critical problem known as the objective mismatch problem.
So, what is that? Well, it's basically when the specific goal you give the model during its training doesn't actually line up with the real-world goal you really want it to achieve. Think of it like this. The model gets a perfect A+ on its homework, which was, say, predicting the next video frame, but then it completely fails the final exam, which is actually succeeding at a task in the real world.
And here's why this matters so much. Imagine a world model for a self-driving car. It might be 99.9% accurate at predicting the next frame of video. Sounds great, right? But what if that tiny 0.1% where it fails is always at the critical moment a pedestrian steps out onto the road? The model can be almost perfect overall, but in the one moment that counts, it's catastrophically wrong.
And that's not the only issue either. You also run into problems like compounding error. That's where tiny little prediction mistakes start to build on each other and they just snowball over time until the AI simulation is complete nonsense. Then you've got something called latent state drift. That's when the AI's imagined world just slowly loses touch with reality. And my favorite is when the AI actually learns to cheat its own internal simulation, finding these weird loopholes in the physics it learned that just don't exist in the real world.
So yeah, there are some pretty major challenges here. But despite all of them, this field is just moving forward at an absolutely incredible pace. We're seeing it scale up from these small, contained game environments to models that are trying to simulate our entire physical reality.
We're really seeing the beginning of a new era. The era of what are being called foundation world models. We're talking about massive systems, things you've probably heard of like OpenAI's Sora and Google's Genie. These things are trained on just insane amounts of video data. And their goal? Well, it's nothing short of creating a general-purpose simulator for the physical world.
And the results we're seeing already are just mind-blowing. So get this. There's a robot called Daydreamer. It spent hours and hours practicing and failing entirely inside its own simulated world. Now, how long do you think it took for that robot to translate all that dreamed-up learning into the real world? Just 60 minutes, 1 hour. That's all the real-world experience it needed to learn how to walk.
I mean, the potential applications here are just enormous. You can generate infinite training scenarios for self-driving cars, right? Safely test them against all sorts of dangerous situations that you'd never want to test in real life. You could teach a robot how to do a super complex task entirely in a simulation, which would just drastically cut down the time and the money you'd spend training it in the real world. This is really the shift from a reactive AI to a truly proactive one.
And that brings us to our final and maybe most important question. We are standing right on the edge of creating an AI that doesn't just process information about our world, but actually builds a fundamental understanding of it, an AI with foresight. So really, the question isn't if we can build them anymore. It's what happens when we do. If an AI can truly understand our world, what will it decide to build in it?